For the introduction, and thank you for the invitation to this conference in honor of Philippe. So I met Philippe at the very beginning of my career in research. At that time, I was finishing a master's in probability, and I was visiting MSRI in Berkeley. And Philippe, you gave a set of wonderful lectures on cluster algebras, T-systems, the octahedron recurrence, how to see it as an egg box that you pop. And well, several years down the road, I started working on these topics, so you will see them in this talk. You will see maybe the egg box at some point also. And also I learned from Philippe that theoretical physicists are nice people to talk to. You know, I was coming from probability, and here I am now in this lab. So that was a great influence on me, and more generally, I think you've been inspirational for many generations of young mathematical physicists, not just by your discoveries, but also by your generosity to explain several things and spend time with younger people. So thank you for all of this. So the talk of today will be several joint works with Niklas Affolter, who is a postdoc in TU Vienna, Terence George, who is a postdoc at UCLA, Max Glick, who is now working for Google, and Pasha Piliavsky, who is at the University of Minnesota. And my goal in this talk is to describe a framework which generalizes two classes of discrete integrable systems. On the one hand, you have discrete integrable systems associated to the dimer model on the torus that were introduced by Goncharov and Kenyon about 10 years ago. And on the other hand, you had many integrable dynamics in geometry, particularly on spaces of polygons, that have been studied for several decades. And these two were more or less separate communities until recently. And the framework that I want to present is the framework of triple crossing diagram maps, and it provides a common generalization for these two classes of discrete integrable systems. So I will start by describing discrete integrable systems associated to dimer models on the torus. So I'll be following roughly work of Rick Kenyon and Sasha Goncharov. So the dimer model, it comes from probability. The setting, the most common setting is that you have planar bipartite graphs, meaning that you can color the vertices in black and white. So you've already seen bipartite works, bipartite graphs today, so I'm not going to give details. And the setting is that each edge carries a weight. When you do probability, these edge weights are positive real numbers. But when you do integrable systems and geometry, these edge weights are non-zero complex numbers, and this will be the setting of this talk. But so what do you do with this in probability? In probability, you look at dimer coverings of the graphs. So a dimer covering of a graph is a subset of edges such that each vertex is covered by exactly one edge in this subset. So this graph has 3 dimer coverings, and the weight of a dimer covering is given by the product of the edge weights. And in probability, you have a Boltzmann probability measure where you pick one dimer covering with probability proportional to its weight. So when you have a collection of edge weights, it gives you a Boltzmann probability measure. But it may be the case that 2 different collections of edge weights give you the same probability measure. So the invariant in this are the so-called face weights. For every, oops, it's not very accurate. For every face, you are going to take the alternating product of the weights around the face. So you go in a counterclockwise order. When you go from a black vertex to a white vertex, you put the corresponding edge weight in the numerator. And when you go from a white vertex to a black vertex, you put the corresponding edge weight in the denominator. So this is what I call face weights, alternating products of edge weights around faces. And two collections of edge weights induce the same Boltzmann probability measure if and only if they have the same face weights. So you have, it's a bit like electrical networks. When you want to compute the equivalent resistance for an electrical network, you have some local moves that help you have a simpler network. You have like a series parallel move and also star triangle move. In the case of diamond models, you have two local moves that help you reduce your system without changing the correlations away from the place where you do these moves. The first of these two moves is called the spider move. So whenever you have somewhere in your graph a face of degree 4 like this, and let's suppose for simplicity that the two black vertices around this face have degree 3, so they have just one other neighbor. But in general, you don't need to assume this, but it's just to make the picture a bit more symmetric. Then you can replace this square face by this one. So you are deleting these two black vertices, replacing them by these two, and there are new edge weights around the face that you can compute from the old edge weights. There's some formula. But as I told you, what really matters in probability are not the edge weights, but the face weights. So you can also compute how the face weights evolve. And this is the formula for the evolution of the face weights. And this formula is, these formulas are special instances of mutations of coefficient variables in cluster algebras. This thing is a bit loose. My ears are too big, okay. Thank you, Philippe. No, doesn't work. Thanks. All right, so this was the first local move. The second local move is simpler. It's whenever you have a vertex of degree 2. Let's say it's white, but it doesn't have to be white. Then you can delete this vertex, delete the two edges adjacent to it, and contract them into a single black vertex. So when you do this, the face weights don't change in the graph. And I want to recombine this kind of move, so contraction, if you go from left to right, and expansion, if you go from right to left, you can go in both directions. I will recombine these moves into what I call a resplit move. So I start with two black vertices of degree 3, which are connected by a white vertex of degree 2. And I first contract this white vertex, and then I uncontract it vertically. So I call this a resplit move. And using these two moves, you can define discrete time dynamics on face-weighted bipartite graphs. And in particular, you can draw your bipartite graphs on the torus. And what you will do is you start with one bipartite graph with face weights. You do a sequence of transformations that will bring you back to the same combinatorial bipartite graphs. But along the way, because the spider move changes the face weights, you will get, at the end, new face weights on your original combinatorial graph. So alternative way to look at graphs on the torus are to look at infinite graphs on the plane that are periodic in two directions and whose weights, here I drew edge weights but also face weights, are periodic in two directions. So here you have a fundamental domain, and if you cut along this fundamental domain and you glue the left and right side and the top and bottom side, you get a torus. So here is an example with the square grid. So this is the way people usually draw the square grid. I prefer to replace every black vertex by this picture, so I'm doing an expansion of this black vertex. So I will draw my square grids like this. then whenever I see some pattern like this, everywhere in the graph, I will replace this simultaneously by that kind of pattern. So I'm doing spider moves everywhere at the same time. So this is possible because these things commute, if they are sufficiently far away. Then I'm going to do this resplit move everywhere I see this pattern. I turn it into this one. So I get this. So this graph is almost the same one as the one that I started with, except that there's a shift. So if I do this twice again, spider moves everywhere, then resplits, I get back to exactly the same graph. So if I do 4 times this sequence of transformation, I get back to my original bipartite graph, but my phase weights have changed. So in general, so this is just the square grid example, but you can do this for any bipartite graph on the torus. In general, these discrete time dynamics are integrable. What does it mean? It means that they have sufficiently many conserved quantities, and these conserved quantities have some nice structure. So behind this, so they Poisson commute, and we have some spectral curve acting in the background, and the motion is translation on some high-dimensional torus, the Jacobian of the spectral curve. This high-dimensional torus has nothing to do with the physical torus on which the bipartite graph was drawn. There's 2 different meanings of the word torus. Several people have worked on that since Goncharov and Kenyon. And in the case of this diamond integrable system, we have a nice interpretation for these conserved quantities as partition functions for some dimer covers with some prescribed homology class. So I'm not going to go into the details. You don't see what homology is doing here, but just trust me. So that was the first story. Oh yeah, and I wanted to add something, that an important tool in this business is something we saw in Rick's talk. It's the Castellane matrix. So the Castellane matrix, as Rick explained, is essentially the black to white adjacency matrix of the graph. You need to add in some technical signs, let's say. And also, since my graph is on the torus, you see here, whenever I have an edge that crosses this vertical boundary of the torus, I multiply by either z or 1 over z, the corresponding edge weight. And whenever I'm crossing the top boundary, I multiply by either w inverse or w, the corresponding edge weight. So all in all, I get a matrix whose entries are Laurent polynomials in z and w. When I take the determinant of this matrix, what I get is a Laurent polynomial in z and w. And if you look at the coefficients of each monomial in z and w, this Laurent polynomial is giving, these are the conserved quantities. So this Laurent polynomial is the generating function of the conserved quantities for this diamond integrable system. So on the one hand, we have this diamond integrable system, which is quite well understood. And on the other hand, we had a zoo of many discrete integrable dynamics in geometry, and often it was treated case by case. And our goal was to provide a kind of common framework for all these dynamics and to prove in a unified way that they are all discrete integrable. And the way to do this is to somehow relate them to the dimer model. So I'm going to do this in the second part. I'm going to introduce the framework of triple crossing diagram maps. Basically, it's bipartite graphs that are enriched with some geometric structures. So I'll be following 2 papers, with one with Niklas Affolter, Max Glick, and Pasha Piliavsky, and the second one with Niklas Affolter and Terence George. So a triple crossing diagram, or for short TCD, because as Christian noted in physics, we like acronyms, So a TCD is just a bipartite graph where all the black vertices have degree 3. That's all. And then I'm going to introduce some geometry. I'm going to add some points in the picture. So here I'll be using projective geometry. So my space is the complex projective space of dimension m, CPM. So for those of you who are not familiar with projective geometry, you have the vector space Cm plus 1, And the space of lines, of vectorial lines in Cm+1 is by definition the projective space CPM. So a point in CPM is a vectorial line in Cm+1. And saying that 3 points are aligned in projective space means that the corresponding 3 vectorial lines lie in a common plane in Cm+1. That's more or less all you will need to know about projective geometry for this talk. And well, if you want to visualize maybe more easily this, you can think of it as affine space to draw some pictures. You'll see I'll draw some pentagram map later, because you just take an affine chart of the projective space, and locally it looks like affine space if you want to picture it more easily. So I start with a triple crossing diagram, a TCD, and to each white vertex, so I have black and white vertices, to each white vertex I attach a point in CPM. So I fix some M, and I work once and for all in some projective space CPM, and I attach a point to each white vertex, and to each black vertex there will be one condition. So the black vertex is of degree 3 by definition of a triple crossing diagram, and my condition is that the 3 points attached to the 3 neighboring white vertices have to be aligned. And for these, we call this a TCD map, triple crossing diagram map. For these TCD maps, just like for the diamond model, I have 2 local moves. The first one is again the spider move. So here, this time you see that I have a face of degree 4, but I really need my 2 black vertices to be of degree 3. So that's why I chose that picture in the first part. Whenever you have a picture like this, what does it mean? This black vertex tells you that the point P1 lies on the line connecting P2 to P4. And this black vertex tells you that the point P3 lies on the line connecting P2 and P4, so the same line. So this picture just means that all the 4 points are aligned. So you can replace it without losing any information by this picture, where you draw the quad differently. And when you do this, it looks trivial like this, because you're not changing the points of the TCD map. It's what we call a reparametrization. But you will see once we have phase variables, things become non-trivial. And you have a second move, which is the resplit. So recall that for the diamond model, the resplit seemed trivial in the sense that the phase weights didn't change. Here's the opposite. The points are going to change. So you start with 2 black vertices of degree 3 connected by a white vertex of degree 2. What does this black vertex say? It says that P is on the line P1, P2, and this one says that P is on the line P3, P4. So basically you have a quadrilateral, P1, P2, P3, P4, which is a planar quadrilateral because P1, P2 intersects P3, P4, the intersection point being P. And then when you have this, you can always extend the side of this and you get what is called a complete quadrilateral. You get 6 points. And these 6 points have been known for millennia to be related by this relation, which is the Menelaus theorem for complete quadrilaterals. So this is where the octahedron recurrence appears in this talk, in this guise. You have P1, P2, P3, P4, which are the 4 points, let's say, at time 0. Below it, you have P, let's say, at time -1. That's the wind. I cannot do anything about this noise. And then you pop the egg box, and you get P prime at time 1. Somebody's calling. So this, this is incidence geometry when you are in dimension at least 2. You can intersect the lines. When you are in dimension 1, you cannot do incidence geometry, but you still have this formula that you use as a definition to define the new point P prime. So these are the 2 local moves for TCD map that are exactly the same as the 2 local moves for diamond models. So for diamond models, we were looking at bipartite graphs on the torus. In the case of TCD maps, to have our integrable systems, we are going to look at TCD maps on cylinders, more precisely on infinite cylinders. So this is a picture of an infinite cylinder. I'm gluing the top with the bottom. And moreover, you see that the graph that I'm drawing on my cylinder is periodic. The bipartite graph is periodic. How about the points? For the points, oops, this one. For the points, I require that the points are quasi-periodic, meaning that if I take a slice like this, it's like a fundamental slice of my infinite cylinder. If I have this point, which is P, then I get the point in the next fundamental slice by multiplying by, so PGL m plus 1 is the space of isometries of CPM, the projective space. So it acts on the points in CPM. And I go from one fundamental slice to the next one by multiplying by m. So here it's mp, then m squared p, and I can go backwards also. It will be m inverse p, m to the minus 2p. So my points, my graph is periodic, and my points are quasi-periodic. And this is what I call twisted TCD maps. And we can go from TCD maps to dimers. How to do that? So recall that in dimers, my setting was that I had bipartite graphs with edge weights and then face weights. So how to get face weights from a TCD map? I start from a bipartite graph, a TCD, with points at each white vertex. And whenever I have a point P1 in CPM, recall that by definition it corresponds to a line in CM plus 1. So on this vectorial line, I can choose any vector, non-zero vector. This is called a lift, V1 of P1. It's non-unique, but I choose one. And I do the same for all 3 points around a given black vertex. So I get 3 lifts, V1, V2, V3. The black vertex says that these 3 vectors are coplanar. So you know from linear algebra that there exists a linear combination of these 3 vectors which vanishes, and not all 3 lambda I are 0. So the numbers that I will attach to each edge will be these lambda I. My black vertex is connected to a white vertex carrying P1. I will put on this edge the scalar in front of the lift of P1. So you see this is not unique because it was a non-unique choice for each lift of each point. It's not unique, there is some gauge freedom, some ambiguity. But here again, we can define some face weights by taking, you know, whenever you have a face, it has even degree, and you take the alternating product of these edge variables. And there's also a technical sign, which is actually the same technical sign as in the Castellane matrix. And then this face weight that you construct like this one is non-ambiguous. It doesn't depend on the choice of lift that you chose on the previous slide. And so since it is somehow canonical, it depends only on the points. You may wonder if you have some direct formula expressing the face weights as a function of the points, and the answer is yes. It can be expressed as a multi-ratio of points attached to white vertices. So I'm not going to give you the definition of multi-ratio, but it is some invariant in projective geometry, and it's a nice product formula. And here in the setting of TCD maps, if you look at how the face weights evolve when you do iterations of moves, it is exactly the same as for the dimer model. So when you do a spider move for TCD maps, the face weights will change, and they will change exactly in the same way as for the dimer model. So you can really see this bipartite dimer model as a marginal of TCD maps. It's a specialization. It's not too special, it's still very general, but TCD maps are slightly more general than bipartite dimer models. So to summarize, in the first part, in the first part, I discussed bipartite graph with phase weights, evolving according to some moves. In the second graph, in the second part, my bipartite graphs were carrying points in CPM. And again, these decorated graphs evolved according to some moves. And from the points in CPM, I could compute in the second part the phase weights. And it was the same evolution as for the bipartite diamond model. And the settings were slightly different. In the first part, my bipartite graphs were living on the torus, whereas in the second part, they were living on an infinite cylinder with a periodic graph, but with quasi-periodic points. So how to use this to apply it to some integrable systems in geometry, particularly dynamics on polygons. So the dynamics on polygons that are usually considered are not for closed polygons, but rather for twisted polygons. So what is a twisted polygon? What is a closed polygon first? You have an n-gon, closed n-gon, you have P1, P2, P3 until Pn, and when you come back, it's not Pn plus 1, it's P1 again. So twisted polygon, when you come back after Pn, you have Pn plus 1, which is not necessarily equal to P1, but when you go from the ith point to the I plus nth point, it's quasi-periodic. So it's a quasi-periodic bi-infinite sequence of points, meaning it's indexed by all the integers, negative and positive, and you have some monodromy to this sequence. So the monodromy is an element of PGLM plus 1 of C, which is the space of symmetries of the complex projective space CPM. And this is the meaning of twisted polygon. Pi plus n equals m times pi. And for twisted polygons, there have been many integrable dynamics on polygons that have been defined. And many or almost all of these known dynamics can be realized as some dynamics on twisted TCD maps. And in general, the technique, to prove that these systems, these dynamics on polygons are integrable, is to look at the monodromy and compute some simple function of the monodromy, which will give you the generating function for the conserved quantities. So remember that in the first part on the bipartite diamond model, I said that the determinant of the Castellane matrix, twisted by Z and W, was giving the generating function for the conserved quantities for the diamond model, whereas for the polygons, you are taking the monodromy and some simple function of it to have the generating function for the conserved quantities. How are these two setups related? So this is what we looked at with Niklas Affolter and Terence George. We showed that for general twisted TCD maps, you can write the monodromy matrix as the Castellane matrix of a fundamental slice of the infinite cylinder. And using this, it gives you a relation between the conserved quantities for the diamond integrable system and the conserved quantities for the dynamics on twisted polygons. So this is very general, but we've figured out the computations in two cases. The first case that we were interested in is called cross-ratio dynamics. So I don't have time to describe what it is, but it was some dynamics studied by these people, Arnold, Fuchs, Ismestiev, and Tabashnikov, who showed that it was integrable and computed the conserved quantities. They gave the generating function for them, and they had an open question: does this dynamics have an interpretation in terms of cluster algebras? So by expressing this cross-ratio dynamics in terms of TCD maps, we answer this open question. And there's another very famous dynamics on polygons called the pentagram map, which I will describe in the next slide. And for this one, many things were already known. The cluster structure was known from Max Glick in 2011, I think. And Ovsienko, Schwarz, and Tabashnikov proved the integrability of this map and also computed the conserved quantities. So we rephrased both dynamics in terms of TCD maps and related the conserved quantities to the conserved quantities of some diamond model. Of which diamond model? Well, once we write it as a TCD map, we have naturally a bipartite graph. So it's the conserved quantities of the diamond model on this bipartite graph. So to finish, how much time do I have left? 0, okay. Let me add epsilon if you're, okay, thanks. Let me just describe the pentagram map. So it's dynamics on twisted polygons, but for simplicity, I will describe it on closed polygons, closed n-gons with n equals 6. At time 0, you start with one n-gon. And then you draw the shortest diagonal. So here I connect the first point to the third one, the sixth point to the fifth point. You draw all the shortest diagonals, you intersect them, and when you intersect two shortest diagonals, it gives you a new point at time 1. You do this for all the pairs of shortest diagonals, it gives you your new polygon. So it looks like the polygons are getting smaller and smaller as you draw these diagonals, but these polygons are considered up to symmetries of a CP3, so they're not getting smaller actually because you can rescale them somehow. So you can iterate this dynamics forward by this simple construction, and you can also iterate it backwards. How do? You take two sides, like first side and third side, and you extend them. And you get a new point. But this is when I'm going backwards, so this would be a new point at time -1. You do this for all pairs of sides I plus 2, and you get your polygon at time -1. So this is the definition of the pentagram map. It's very simple, very natural dynamical system. And here's the TCD map for the pentagram map. So first I need to give names to these points. So the points at time 0 that I started with, I call them Pi. The points at time 1, I call them P prime I. And when I go backwards in time, at time -1, I call these P hat I. And this is so what is not clear from this picture is that here you're on an infinite cylinder. You need to extend this in the horizontal direction. And let's just check, for example, this white point, it carries a P4 hat. Where is P4 hat? It's here. So P4 hat should be on the line P2, P3. Is that correct? So you have P2, P3 here. And when you extend this side, you get to P4. And it's also on the side P4, P5. Is that true? P5, P4, you extend it and you get to P4 hat. So at least for one point here is correct, and trust me, they are all correct. And once you have this, so this takes time. Find how to find the right TCD map for a given dynamics, such that when you iterate the local moves, you reproduce exactly the dynamics of the pentagram map. This is what takes time. But once you have this, it's very easy. You do resplit moves. So here you see you can do a resplit move at every white vertex of degree 2. So these ones, all the ones carrying some Pi hat, you get this. So when you do resplit moves, you delete old points and you create new points. So here you are deleting the hat points and you are creating prime points. And you can check again that this is the correct TCD map if you consider just the points Pi and P prime I. And then you do another move, which is, you have here these quadrangles, you do spider moves at each quadrangle, and you get almost the same, almost the same bipartite graph, just shifted by 1 unit. So you apply this twice again, and you get back to your original graph, but with new points attached to it. And okay, so time to conclude. So in the first part, I showed you that on the one hand, you had a very well unified theory for discrete integrable systems associated with diamond models on bipartite graphs on the torus. And On the other hand, we had this disparate collection of integrable geometric dynamics. I discussed some dynamics on polygons, but you also have another area in math where you have such dynamics. It's called discrete differential geometry. There are many discrete dynamics in there, for example, Q-nets. And we managed to rephrase many of these systems in a common framework. So for Q-nets, it was, for example, an open question whether there was an underlying cluster algebra structure. And these TCD maps answer this open question. So this was the purpose of introducing TCD maps. And it provides a powerful machinery to prove in a unified way the integrability of many systems from geometry. I guess the mic doesn't want to work anymore, so my time is up, I guess. And here are the references, and once again, happy birthday, Philippe.
Questions? Comments?
In what way are TCD maps more general than dimers?
You can prescribe points on the boundary, and then using the face weights, you can propagate. But the dimension of the space is slightly larger. If you look at these twisted TCD map on a cylinder, and you compare it, if you close the cylinder at the dimension of the diamond model on the torus, it's just one larger. It's very small, the difference. There's one Casimir more, for example, for the pentagram map.
If there are no more questions, then let's thank the speaker again. Also thank all the speakers of the day, in fact, and happy birthday, Philippe.